try to get started here. Sorry for the delay. I'm still getting used to this semester. So last time I told you guys a lot of the, limit laws, right? What were our limit laws? Oh, that one's dead. I wonder if this one's dead. So if we're given, this is important, right? That the limit as x goes to a of f of x equals, let's say, L sub f, and the limit as x goes to a of g of x equals L sub g. And I'm just writing L sub f and L sub g there to save trash. Writing. Then, oh man, look at that. Well, that one's not awesome either. Hopefully one of these works. Well, I could write L sub f plus L sub g, right? But so, and what else was the other property we had? Like the limit, how this one works, of f times g is what? Lim f times the limit of g, right? And what other thing we can do? I messed up the numbering. The numbering was, remember I had like 1, 2, 3, 4, 5, 6 last time. So you don't have to write those down again. I'm just trying to refresh our memories. So the ones I had written down last time were all about like sort of generic patterns, right? Ending with the composition of functions. So past that point in the notes, I also introduced a couple of other sort of more specific limit laws. And we already did one of them, like the limit as x approaches a of x was, what was it? Let me write it down. We did this last time. In fact, I think I concluded by basically saying limit as x goes to a of x equals to a. Then I point out if you have that and you have the product rule up here, you can get the limit as x goes to a of x squared equals to a squared, right? And then like more generically speaking, if you have the limit as x goes to a of, let's say, c0 plus c1x plus da-da-da plus cn x to the n, the way you calculate such a limit is what? You just plug in the limiting value, right? So that one is equal to what? It's equal to so this is proposition 3.39 in my notes, but if you look at proposition 3.39 in my notes, you won't see this formula I'm writing down right now. I've written it in a different way, all right? Let me talk about that for a second. So this is, one of the limit laws that we get to. If we have a limit of a polynomial, we can just plug in the limit point, right? So I wrote this in the notes in a much more compact notation. I called this thing p of x. And I said, okay, so if you have a polynomial, then you take the limit of a polynomial, you just plug in the limiting value. You evaluate, right? That's all there is to it for that kind of thing. So what other kind of functions did you guys talk about in pre-calculus? Do you remember? Well, one of the other things you talked about was like the reciprocal function, right? Like 1 over x, remember? So what's that thing look like? It's like this, right? Y equals 1 over x. And so if you look at the graph of this thing, you can see that the graph's not jumping, right? Except for one point. Where's it jump? It jumps at x equals to 0, right? It jumps from like minus infinity from one side to plus infinity on the other. So there's a vertical asymptote at 0, right? But otherwise, we have the limit as x goes to a of 1 over x equals to what? Just 1 over a, right? This is for a not equal to 0, though. What about fractional powers? What if you had like x to the m over n? Well, the x to the m over n power, it also works out to a to the m over n. This is assuming a is greater than 0. Now, I should remind you, because it may be a while since you've thought about this, but what's the domain of the square root of x? Which x, for what x is the square root of x a real value? We need what? X, yeah, positive, or what else could be okay? Like square root of 0 is what? 0, right? So positive or 0, and so like when we talk about positive or 0, we say non-negative. But you're exactly, you've got 100% of the answer. You're just missing 0. But oh, infinity. Well, see, the infinity's not included, right? This notation. I mean, because I write the parentheses, it's not included. But I mean, less silly comment would be, we don't think of infinity as a real number. So it's, when I talk about domain, I'm asking like which real numbers is the function defined for, right? But now, here's something that students sometimes miss. I mean, I probably would not have been keen to this issue when I was in your place. What's the domain of the cube root of x? All real numbers, very good. So sometimes students want to give me the same answer that I just had up there. Right, yeah, so like a good example would be cube root of say minus 27 is minus 3. Why is that? Because minus 3 cubed is minus 1 cubed, listen to me. Minus 3 cubed is in fact minus 27, right? And so that means that the cube root of minus 27 is minus 3. So we can take cube roots of negative numbers. So there's a big difference between cube root and I mean, here's basically the story. So this is y equals x to the 2n, right? Grossly speaking, that's what the graph of y equals x to the 2n looks like. What's the inverse function of that? See, you should realize that's a loaded question because square root of x, well, x to the right idea. I mean, you're not wrong, but we would say x to the 1 over 2n, right? Like that would be the inverse function of that, or we could write. But this is our other notation, the 2nth root. But that's not entirely honest. Like that's not the inverse function of this, right? Because when is a function invertible? Do you guys remember? It has to pass the horizontal line test, right? Does this pass the horizontal line test? No, it does not. And the graph of these guys basically looks like this, crudely speaking. And if you look at that, that's not the inverse function of the whole graph x equals to 2n. It's the inverse function of just this piece. So like technically speaking, this even root power is the inverse of just the positive part, positive domain of the x to the 2n function. What I'm trying to say is the domain of these guys is also 0 to infinity. But in contrast, there's a big difference. If we look at x to the odd power, it does pass the 1-to-1. It is pass the horizontal line test without restriction. So we can talk about the inverse function for an odd power without like restricting it down like that. And so the graph of the inverse function is just flip it on its side, basically. And this is what y equals x to the 1 over odd power looks like, which in the index notation is this. So that could be like a cube root, a fifth root, a seventh root. All these things kind of grossly resemble that. And so I'm being a little bit nonchalant here about what the graph of x to an odd power looks like, right? Because what does x to the first power look like? It's a line, right? Y equals x. But this is kind of what the cube looks like. And if you looked at x to the fifth, it kind of looks like this. So this is the kind of graph, you asked me about a graphing calculator a couple minutes ago. This is what set me on this path. These are the kind of graphs I think you should be able to make without a graphing calculator. Like you should have in your mind's eye, that's what x squared looks like. That's what x to the fourth looks like. That's what x to the fifth looks like, you know? So anyway, how about x to the m over n? What's that? Like what's x to the 2/3 look like? What's the domain of x to the 2/3? So it turns out, because of this annoying issue here, when we have a fractional power, just to stay out of trouble, we're only going to look at like positive bases, positive inputs, because otherwise we have trouble with the even roots, right? And if you did something like x to the, well, anyway, I'll just stop talking about that. There's nothing much more for me to say, but okay, so what are these? What are square roots and things like that? These are called algebraic functions, right? So in a nutshell, here's the theorem. If you have an algebraic function, right? What is an algebraic function? It's a function whose formula is built from like addition, subtraction, multiplication, square root, cube root, roots, things like this, right? Algebraic operations. If you have a function whose formula is constructed from a finite number of algebraic operations, then what ends up happening is you can calculate the limit by just plugging in the point, provided that the point is a point which doesn't provoke any issues of arithmetic in the sense of like no division by 0 and no even root of a negative number. So, and so yeah, that's a theorem essentially. So here's the theorem. Limit as x goes to a of f of x equals to f of a for algebraic function f of x, provided formula f of a is nice. And that's not a very precise mathematical statement, but by nice I mean what I just said, like no division by 0, no square root of a negative number, all right? Let me give you a specific example of that. So a specific example of that would be something like, let's calculate the limit as x goes to 2 of x plus the square root of 1 plus 1 over x squared over x minus 7. So the formula I just wrote is an algebraic formula. It's an example of a function whose formula is an algebraic function. I mean, this is an algebraic function because I got a division, I've got an addition, I've got a square root, right? These are algebraic operations. This is the formula of an algebraic function. And what this theorem I'm telling you says is just try plugging in the number. And if it works, it works. If it doesn't, well, we'll talk about that in a second. But 2. So my first line of defense in calculating a limit, which looks kind of scary, is just to plug in the limiting value. What's 2 squared? That's 4, right? And 2 minus 7. So there you go. Whatever that number is, I mean, I can simplify it just a little bit. What's 1 plus 5/4? It's what? Excuse me, 1 plus 5/4. I'm telling you the answer. 1 plus 1/4 is what? 5/4. What's the square root of 5/4? I'll write it out. Yeah, square root of 5 over 2. And 2 minus 7 is minus 5, right? So, in fact, we could write this as 2 plus 1/2 square root of 5 over minus 5. And you're like, fractions offend me. Why have two fractions when you can just have one? How can you make that half disappear? What would you do? How would you What's that? Square, yeah, well.
So,
mm-hmm.
so say when, so like the 2 plus the 1/2, the square root of 5, instead of doing that, could I just possibly leave the square root of 5 on top of 2, or?
Oh yeah, that's the same.
Okay, I just wanted to
like, yeah, 1/2 square root of 5
yeah.
is equal to square root of 5 over 2. That's, like, we always have that option. It's like, just generically speaking, A over B is equal to A times 1 over B. So oftentimes I'll use that identity if I don't want to write like the fraction big, so to speak. I mean, but my point to you guys would be here, if I want to get rid of the half, I would multiply by 2 over 2, right? If I multiply this fraction by 2 over 2, then I distribute the 2 through, right? I get 2 times 2, which is 4. This 2 cancels the half and just leaves me plus square root of 5. And yeah, negative 10 downstairs. And so there you go. Now, listen, everything past this point right here was not calculus. It's just like a question of do you eat with, which fork do you eat with first at dinner, right? I mean, it's like, it's etiquette. And I wouldn't take off points if you just got this far, probably, and put a box around it. Like, this is a totally legit answer for this question. All right? But this is a better answer that mathematicians would tend to like you to write, something like that, just cleaning up your, just kind of house, tidying things up, really. So this is an example of that theorem. All right? So I ask you again, what other functions did you talk about in pre-calculus? How about pre-calculus trigonometry? You did what? Sine and cosine, right? Sine, cosine, tangent. So let's talk about sine and cosine, right? So if we look at the graph of sine, right? And suppose x is in radians. In order to calculate the limit of sine, we need to do like a little bit of geometric I would say argumentation, but I suppose what I'm about to do is more bullying than argument. I would claim that you could prove, and I'm not going to do this today, but if you look at the line y equals x, right? And you were to zoom in on that and look at sine x, right? You can see that, in fact, we have the following inequality. We have that the absolute value of sine x is less than or equal to the absolute value of x. Provided that we're, within, here to here, for sure. It actually might continue to be true, but I'm particularly interested in this for 0 less than or equal to x less than or equal to pi over 2. All right? So I'm just arguing that that's geometrically clear. Now, if you wanted to give, if you wanted to make that argument precise, what would you look at? Like, how should we actually go about proving that? Let me just take a minute to talk about that briefly. See, I saw on your notebook you have this handy dandy. Can I steal for a second?
Yeah, you can.
See, he has this Yeah, unit circle, right? And that's the kind of thing we want to look at to make this argument. You'd look at, because we could look at the unit circle, right? And I think you'd look at, well, again, I wasn't going to make this argument. So, but if you look at this unit circle, we'll come back to this unit circle thing a little bit later in the course. Let me just kind of wait for that. But this point right here would be what? It would be sine theta, cosine theta. If you make that theta. And, but here we're using x both as, both in the sense of the x coordinate and the angle. So this inequality would come from looking something at putting theta equal to x. And if you do that, well, you can, you have sine x, cosine x in that context. And I said I wasn't going to prove this. Let me stop. Anyway, you just keep playing with these things and you can come to a specific proof of this. Look, how about this? Since I'm being a little bit vague, I'll give you a couple bonus points if you can find a geometric proof of this for me sometime soon, okay? It's not in my notes, I just claim it. And I do think it's geometrically true if you look at the graph. You can see that, in fact, the absolute value of x is a little bit above sine x right there, okay? All right. One of my principal vices is when I start trying to explain something, it's very, very hard for me to walk away from it and say, okay, so, you guys figure it out. Are we all on board that makes sense? The absolute value, that x is a little bit above sine x, it's okay? So let's look at my claim is that the limit as x goes to 0 of sine x is equal to what? I mean, there's no jump in the graph of sine, right? So if intuition serves us correctly, it should be whatever that value is right there, which is 0, right? Sine of 0 is 0. So we expect that should be 0. So let me prove it. We're going to go back to that epsilon delta definition again. So let epsilon be greater than 0. And it turns out if we just choose delta equal to epsilon this time, it'll work out just fine for us. Suppose 0 less than absolute value of x minus 0 is less than delta, right? That's what we get to control. We suppose we're within delta units of 0. And then what are we supposed to, we're supposed to consider the value of the function minus the limiting value. In this case, sine of x minus 0, right? But what did I just tell you? Geometrically, the absolute value of sine of x is less than or equal to x, right? So this is less than or equal to absolute value of x, which is what? Which is less than delta, which is equal to epsilon. And so this is all you need to do to prove that the limit as x goes to 0 of sine of x is equal to 0. All right? In other words, and 0, of course, is sine of 0. So I would point out that this is just part of this continuing storyline that for nice functions we just plug in the limiting value, right? So how about for other values other than 0? How would you calculate the limit as x goes to a of sine of x? So I'm getting a little bit ahead of the story, but let me just, for the sake of not dragging this out too long, the details are in the notes, but you can also prove through a similar argument and a corresponding estimate, geometric estimate for cosine, you can prove that the limit of cosine of 0 as x approaches 0 of cosine is what? It's cosine of 0, which is in fact 1. So you can, I argue from the inequality absolute value of cosine of x minus 1 is less than or equal to absolute value of x. So if you can prove these two things geometrically, then it's easy to establish that the limits of sine and cosine at 0 are what you think they should be. So how do we, so this what I'm about to show you is a pretty neat trick. We can make a substitution. If we let x minus a equal to h, if we let x minus a equal to h, what's x equal to? X would be equal to a plus h, right? And if x goes to a, we see what? H goes to what? If x is approaching a, and h is equal to x minus a, what is h approaching? So I'm saying let us introduce a new variable called h, right? H is equal to x minus a. Maybe, if you like, I could say let h equal to x minus a, fine there. Which comes first, egg or chicken? All right, very good. Now what happens as x goes to a for h? Well, yes, x is equal to a plus h is also true, but how about the limit? What does h go to as x goes to a? Ignore this line for a second. Just are there kids shouting outside? Infinity? Opposite of that. Sort of opposite of that. No, if x goes to a, then x minus a goes to a minus a, and a minus a is 0. So h goes to 0, right? So like if x is approaching a, then these things are getting very, very close to each other, so when you subtract them, they're just 0, which is to say that that's going to 0.
So you took x, like x is equal to a plus h, right? And plug in where x is in the first place.
How about this? Let me.
I'm getting confused about it.
The thing is, I have gone from one thing to another. Let h equal to x minus a. The limit as x goes to a of h is equal to the limit as x goes to a of x minus a, which is what? According to our limit laws, that's a minus a, right? Because we can break up a sum of limits to the limit of the sum. We can pull a minus out. The limit of x as x approaches a is just a. So a minus a is 0, right? So in other words, I can rewrite this. H goes to 0 as x goes to a. What I'm trying to tell you is we can trade a limit as x approaches a for a corresponding limit of h going to 0, provided we replace x everywhere it appears with what? We replace x with x equals to a plus h. So if I put a plus h in the place of x, and I let h approach 0, that gives me an equivalent version of the same limit. So this is really just a special case of the substitution law I told you guys about last time. But there it is. Now, question, can you guys tell me what sine of a plus h is? How do you break up a sine of a sum? What's the rule? Do you remember this from pre-calculus? Maybe not. So the adding angles formula is sine A cosine H plus cosine A sine H. Right? This is the adding angles formula for sine. But what do we know about the limits of things involved there, right? I've already argued, I claimed anyway, that the limit as h goes to 0 of cosine of h goes to 1. And I argued that the limit of sine h as h goes to 0 is 0. So what do we have altogether here? We have sine of a times 1 plus 0 by the limit laws. We just get sine of a, which is a completely unsurprising result, right? It says that this sine function is nice. Whenever you take the limit of sine as you approach a point in its domain, you just plug in the point. Okay? And guess what? The same is true for cosine. I think in my notes I proved it for cosine. I may have just worked one of your homework problems. Uh-oh. Yeah, on page 121 in the notes, I have the corresponding argument for cosine. I may or may not have remembered to make this one of your homework problems. If I did, I'm sorry, I may have just kind of worked it. But again, bonus points if you can give me like, right triangle trigonometric geometric arguments that prove this. I think you can do it. It's just a matter of drawing the right picture. All right, I shut up. So, okay, what else is there? I've almost exhausted. What happened also at the end of your first pre-calculus course, if you took it here? I taught this one last semester, so I know. 113, pre-calculus algebra. Nobody took it here? We took it a long time ago. You'd like to forget about it? No. We also talk about logarithms and exponentials, right? So it is in fact true that the limit as x goes to a of, let's say, b to the x, because I usually use a for the base here, but I'm using a for the limit point. So let's say b to the x. Guess what? It's just equal to b to the a. And I have some arguments for showing that's true in the notes, but I'll just kind of leave it at that. Now, it's also true that the limit as x goes to, let's say a, of log base b of x is equal to log base b of a. But I really have no right, like the proof of this comes later in my notes. It's not in the part I've provided for you yet. It's actually kind of a pain to prove the limits of the inverse functions. It takes some work on my part. But I'm not going to do that today because I want to talk to you about problems like your homework. So that's pretty much all I got to say in terms of basic limits. Let me just, to summarize, what am I saying? To calculate the limit of a function, if the formula makes sense, you just plug in the limit point. Game over. It's not bad, right? So open the floor up to you guys. What do you have questions about? Or would you like me to just do problems like those ones, like similar to the ones in the homework, but not the same?
Yeah, can we do that?
Yeah, I can start with that. I am going to one other criticism I'll make of the course so far is that, I've spent a little bit of time talking about these epsilon delta proofs and so forth, and in some sense that's not great because it's not really where this course stays, right? So what I mean is what I mean is like the techniques of proof that like this proof I gave today, showing the limit of sine, that's not really tracking with what you're responsible for in this course. So in some sense, it's not a good proof to show you, right? But I do want to show you that there's thinking behind these things. But technically, like, we test that kind of thinking more in the real analysis course here, all right? In contrast, the examples I'm about to do are like right in the sweet spot for the first test. They're like what the first test is mostly about, okay? Because this is like using the limit laws to do calculations, which are not just, well, there will be problems on the test which are as simple as like that example, in the sense like you just plug it in, you're done, right? But there'll be other ones that require algebra, like the following. Let's calculate the limit as x goes to 2 of x minus 2 over x squared minus 4. If I inadvertently do one of your homework problems, it's not on purpose. It's just that I'm a creature of habit, you know? So first thing I try to do is to plug in the limiting value, the limit point. The limit point here is 2, right? Plug it in, what happens? We get 0 on top. We get 0 on the bottom. So this initial limit has what we call type, 0 over 0, right? I don't say it's equal to 0 over 0 because that doesn't make sense. So I use a weasel word. It's type 0 over 0. All right. So what do I got to do? Something else, right? So what we do, what would you guys suggest I do? Can you guys factor the denominator for me? X minus, right idea, wrong number. X minus 2, x what? X plus 2. You had the right idea, just, yeah. Because 4 is really 2 squared, right?
Oh, yeah, I did the math a little bit.
It's rusty. You say it's just been a minute since you've done math?
It's been like 7 months.
7 months. Well, that's no way to live.
It is. It was great.
It's not all. Like, I tried that last year. Like, I spent...
The minute they brought letters and algebra.
I'm telling you, like, the year I spent, like, not teaching math, I would go to the restroom and then I'd just be alone with myself and then thinking about the fact I wasn't doing that much math, and like the walls start closing in on me. I feel horrible. It's just like crushing weight. It's just... They're all dead, so. It need to be. Yeah. Let's see here. I guess I should never admit to inventing new math. I may get my beating. Let's see here. Although I think that's generally good advice for society. More people need to be whooped. But, so okay. So then what? And why can you do that? There's not a sign. Right, yeah, that's true. This has to be multiplying everything in the denominator for that to work, right? Right. But what else do we know? What's that? Yeah, we just cancel. The reason that we can do this step right here is because, remember, x is not equal to 2 in the limit. Like, technically speaking, in algebra, you can only cancel x minus 2 with x minus 2 when x is not equal to 2. When x is equal to 2, canceling x minus 2 and x minus 2 is just nonsense. So, but with the limit, we are logically justified in making that cancellation. And now, see what's happened? What kind of limit do we have now? So this is no longer type 0 over 0, right? Not 0 over 0 anymore. And you say we just plug it in, right? Which is what, 1 over 2 plus 2, which like you said is 1 over 4. What do you think?
That is a lot easier than what it looks like.
Mm-hmm. Yeah, see, and notice there's not an epsilon or delta to be seen in sight, right? Because we're just using limit laws in algebra. Okay? Let's see here if we could come up with another example. How about limit as x approaches 3 of, goodness gracious. Try to come up with an example which is not exactly the same example. Let's see here.
Oh, wait, can I ask something?
Sure.
Homework, say if we wanted to write it out, you want us to draw the graphs too, right?
Mm-hmm.
Okay, I just want to make sure.
Yeah, that's the annoying part about. Now, if you just want to print out the graph and like paste it on top of that or something, that's fine. All I was trying to say is like, I don't want to try to grade like a page with yes, no, 13, 42. You know, like I need the statement and the work. Although sometimes there's no work, right? Some of those I ask you like, what's the limit of the function at the point? What's the work? The work is 7. I mean, once we have an intuitive visual understanding of limit, we just can look at things by examination, right? How about I forgot my. You're fine. I'm trying to come up with one that's trickier. X goes to 3. Let's make that well, yeah, fine. 3 of 1 over 3 minus 1 over x over, x plus 3. X minus 3, rather. And then example 3, I give you, one second. I'm going to let you guys work on that for just a second. Let me go make sure that, because technically we don't have this room right now. Could get booted. Forgot my mask. All right, I'm back. Sorry about that, guys. It's for a good cause. So what did you guys do? Any ideas? Please work. Oh man, how long have these been sitting in that? Look at this. trash. So what is, again, this is type what? Type 0 over 0. Was 0 over 0 equal to 1, by the way? It was not. It was 1/4. Type 0 over 0 is called an indeterminate form. And the reason for that is if we look at different examples of type 0 over 0, we'll get different answers. So like if it's type 0 over 0, that means we don't know what's going to happen until we work out the algebra. It's indeterminate.
I just got the bottom is 0.
Oh, just the bottom? Is the top not 0? Did I mess it up? If we can just plug in the point, then hey, we can just plug in the point.
Oh, no, I'm stupid.
Nothing?
I'm stupid.
Oh. Well.
I put, I substituted the 1 for 3. I don't know.
Oh. It's okay. So, any ideas? What we're going to do? So what I'm going to do, man, how long has that pack of, look at this. I wonder how long, this pack of marker must have been sitting in that drawer for like 5 years or something stupid. Look at this. Golly. Man, that's aggravating. I'm going to have to go to Walmart and buy some fresh ones. I'm sorry, guys. I got some at home, but I thought I have a whole pack here. And goodness, it's just aggravating. It's probably more aggravating to me than to you, so I'll just, all right, so x minus 3. This 1/3, how can we make a common denominator here? How about this is, you change the x to a 3, kind of, like how about x over 3x, right? Minus 3 over 3x, right? So what I'm saying is multiply this one by x over x, multiply this one by 3 over 3, so that they have a common 3x as a denominator. Once they have a common denominator, then we can subtract, yeah? Now, hey, if you want to look at the algebra a different way, I'm fine with that. This is just how I see it, okay? So that's x minus 3 over 3x. So then what? Since x is not equal to 3 inside the limit, we're allowed to cancel the x minus 3 factors. Right? Like so. That's all that marker's good for. And we're just left with what? Yeah, limit as x goes to 3 of 1 over 3x, which is, see now it's no longer indeterminate. We're at a point where we can just plug in the limit point, right? 1 over 9. You got it. So check that out. Is 0 over 0 apparently works out to 1/4. It also works out to 1/9. What else is it going to work out to? Yeah, we'll see. Sometimes it won't work out. Sometimes it's going to blow up. Sometimes it just won't exist. All right? See if I can find a... Let me try to do an example here with some sines and cosines and such. Example 3. How about if we have the limit as theta goes to 0 of, let's say, cosecant theta minus cotangent theta. So first thing, you just told me 7 months, right? So I think I owe you at least the definition of cosecant and cotangent before we go any further, right?
Is it the inverse of sin?
Yeah, the multiplicative inverse of sine, right? And cotangent theta is what?
The inverse of sin?
Yeah, it's 1 over tangent.
But it's sin. Is it cosine over sine or sin over?
It is cosine over sine. In contrast, tangent theta is sine theta over cosine theta. So what happens with, tell you what, to make this a little bit more precise, let me make this 0 approaching from the right. So let's rewrite this limit in terms of sine and cosine, yeah? So we're looking at 1 over sine theta minus cosine theta over sine theta. That's, here, let me give this thing a label. I use Pac-Man. There we go. So Pac-Man equals. So one of the things I try to teach students is to not like,
So that's what you think?
not yet, no,
Oh,
is to not just like let expressions be floating. So we want to connect our ideas carefully. So like one of the principal shortcomings of the way you've written work up till now likely is that you just like write an equation, write another equation, write another equation, just kind of like shotgun all over the page, a lot of people. And it's not clear which one comes next and which ones are actually equal. So I try to write work in here where, you know, just like I have equality here because those things are equal. And I don't write equals unless it's equals, right? If it's some kind of, not an equality step, but some kind of other step, I try to write a sentence that says what I'm doing. So, you know, I don't like take off all the points if you make a notational error, but I will take off some points to try to encourage you to like, you know, denote mathematics better. That's one of our goals, but not a big deal. But here's just like a little slice of it. Like I wrote Pac-Man here and here just to communicate to the reader I'm still working on exactly that limit. You know, it's just a silly little thing, but what's the trouble with this one? What happens to sine? What's the graph of sine look like? Oh, yes, right there. So what happens as we're approaching, thank you. We're approaching theta from the right? We're like in here. It's going to what? It's going to 0, right? It's a small positive number. What's 1 over a small positive number equal to? A fraction, yeah. Like 1 over 0.1 is 10, right? 1 over 0.01 is 100. 1 over 0.001 is 1,000. 1 over 0.0001 is 10,000. And it just gets worse from there. This is going to infinity. And this ain't no better. Because that's something that's going to 1 over something that's going to infinity. 0, which is, again, infinity. So what we've got is positive infinity minus another positive infinity. This is type infinity minus infinity, which is another indeterminate form. So what are we going to do? So we didn't have to work very hard to make a common denominator this time, did we? Because it was just there. We just had to understand it, right? And then what?
1 minus cosine is equal to, like sine squared theta or something? For some kind of trig function.
Yeah, doesn't that equal a trig function? Like the 1 minus cosine itself?
Maybe, but I don't know right offhand.
It looks very, like,
I thought 1 minus cosine equals sine squared theta, but
Well, oh, you're right that 1 minus cosine squared theta is sine squared theta. And so how can we make 1 minus cosine squared appear? By the way, I think this example, what I'm doing right now, is harder than your homework. In a sense, because it requires this kind of sneaky step. I think we can solve this if we multiply by 1 plus cosine theta. And if you guys hadn't said what you just said, I might not have thought of this. So thank you for saying that. See, because, yeah, like when I multiply this, that gives us what? 1 minus cosine squared theta upstairs, right?
Why would we just randomly multiply 1 plus cosine?
Because you guys told me that,
To make it cosine squared.
yeah, to make it 1 minus cosine squared theta, because then that is a sine theta squared, and that will allow us to eliminate the sine theta in the denominator, which is the troublemaker. See, like, we went from type infinity over infinity minus infinity. We did an algebra step, and what happened? Did it make it not indeterminate? No, it just changed the type of indeterminacy. This is type 0 over 0, because 1 minus cosine is 1 minus 1 as theta goes to 0. I mean, that the numerator goes to 0, the denominator goes to 0. It's type 0 over 0. But because what you guys told me, I think if we multiply by 1 plus cosine theta over 1 plus cosine theta, we're going to be good to go. Because that's going to change this to sine squared theta. And now there's hope, right? Because we can cancel the sine theta with the square, right? And what do we got? And that, my friends, is not a bad actor. Like, we can plug in 0 now. What do we get? Sine 0 over 1 plus cosine 0. Well, you're like, well, we still got 0. Yes, that's true. There's 0 in the denominator, right? But what? Excuse me, listen to me, 0 in the denominator. There's 0 in the numerator, right? Sorry, I got it. 0 in the numerator, which is fine. Sine of 0 is 0. That's supposed to be a 0. I've got a smudge here making it look like theta. So,
That would be the answer.
I would like for, if this sort of thing happens, I would like for you to simplify it just a little bit. I mean, I would like students to write 0 in this case. Cosine of 0 is 1.
Oh, okay.
So 1 plus 1 is 2. All right. Let's see here. Let me take a quick look at your homework. Yeah. So let's see here. Okay. Let me change this problem ever so slightly. First of all, let me make sure I'm not doing your homework exactly. I hope I am not. Okay, good, I'm not. How would this problem turn out differently? Let's see here. Oh, that's not no, that's not quite